And now we're going to move on to the second session of this conference, which is a workshop on exponential random graph model and network simulation. And the instructor of this workshop is Wenyi Shang. On the second day of the conference, Wenyi Shang shared his study of the network aristocratic interactions in Eastern Jing during the 4th century, using data from Shishuo Xingyu, the 5th century collection of historical anecdotes and biographical sketches. To understand the dynamics that generate the structure of the network, Wenyi Shang simulated the evolution of that network. So today's workshop focuses on the methods that Shang used in the network simulation. Wenyi Shang is one of the few presenters here in this conference who came from a natural science background. Wenyi Shang received his bachelor's degree in information management from Peking University in China. He's currently a PhD student in the School of Information Sciences at University of Illinois, Urbana-Champaign. Without further ado, I would like to give the time to Mr. Shang.
Thank you, Professor Chen. I would like to add a small tip, which is theoretically, the information management seems really natural science. It is under the social science discipline. But in any case, yes, I am, among others, less humanist background, though I would like to define myself a humanist. So let's move to the topic. So today's workshop will focus on network simulation and ERGM. I'm going to explain these two concepts later. And so basically the workshop will contain 2 parts. And I'm from the School of Information Sciences, University of Illinois and Urbana-Champaign. And you may contact me at this email address. First of all, the navigation. So I'm going to move back to this page from time to time. And so basically we have 2 large parts of this in this workshop, which is network simulation and exponential random graph models, which is abbreviated as ERGM. And for each of them, I'm going to include 2 parts. The first as introduction, and then I'll move on to the hands-on examples. So I'm going to cover some basic theoretical parts in the introduction, and then move on to hands-on example. I hope you already downloaded Python and R. Even if you haven't, I'm going to showcase it, and you can follow it later in the video, which will be shown after the workshop. So first, introduction about the network simulation. So our first basic assumption about network simulation is social networks are dynamic and reactive models. They have certain structures. So as opposed to random network, some social network are usually created by some, or they have some certain structures and are created by something, so which is behavior. So our second assumption is behavior generates structure. So which means that if we have a social network, it must be generated by some behavior rather than completely randomly generated. Even if random generation is a behavior. So based on these 2 assumptions, the idea of network simulation is to simulate the evolution of the network in order to understand the behavior that generates the network structure. So if we have some assumption that some behavior will generate the structure, then if we know the structure, we can simulate the process and to guess what was the structure, what was the behavior that generates the structure. So we're going a backward logic that based on the behavior generated structure, we'll try to base the structure, base our assumptions on behavior on the results of the structure. So what is the network, as the evolution of the network? So the evolution of the network is the network formation. So which is how the network is initially constructed and how it's changed over time. So it has 2 parts, and we're going to investigate how the network has evolved. And based on our observation here, we're going to try to guess what the behavior it is. So the first very basic model is in the network simulation is random model. What is that? So suppose we have a group of nodes. In my case, the nodes are people, but in social network, they are not certainly not limited to people. For example, you can also assume they are like Xiong Hui presented it is placed in the office. And also, it could be some text. But in any case, in the social networks, where the basic structure of social network is composed by nodes and something connected nodes, which is edges. So suppose we have a group of nodes, but no edge between them initially. And then at each time step, so which is at each time, one pair of unconnected nodes are picked random and get connected randomly. So we have a bunch of nodes, and at each time, we randomly select 2 nodes and get them connected. So each pair of unconnected node has an exactly equal chance to be picked and connected. So there is no specific behavior at all. We are just assuming that everything comes randomly. And how would you suggest? How would you assume this kind of network be like? Or we're disabling chat, so I'm not looking for feedback now, but you can think of it. So if they are connected completely randomly, how will the network becomes after some time steps? And here's the result. So if we are assuming completely randomness, the results will be like that, will be basically like that. But for sure, since it is completely randomly, it has some variations from time to time. But basically, the idea of completely of a random model will be like that. So each node, so the nodes basically will have the similar number of connections, which is edges. So we will show the degrees distribution later. But the basic idea is that if we connect them and pick them exactly randomly, they will have the similar number of connections. So this is the baseline model, which is a very, very basic idea. But in the real world, we have to move beyond random. Since in the real world, the random assumption does not usually hold. Some nodes or people are more likely to be connected or have relationships than others. So here's a real world network. We're disabling discussions, but so if you can, I'll give you 30 seconds to think of what network will this be. So I'm going to explain what is this. So here's the giant component is a large proportion of people in this network, and the smaller ones are the smaller patterns. So for example, here in the bottom right, there are 63 such patterns, which is a blue node, which is a male connected to a female. And we have 12 cases that a male connected to 2 females, and 9 cases of 1 female connected to 2 males. And here there are giant components that more people are interconnected. So you will have your guess, and I'm revealing the results. So it is the structure of romantic sexual relationships of Jefferson High School is in a famous study. So here in this network, we find that most people, or a large proportion of people in the Jefferson High School have interconnected romantic relationships. And we can find some people in this giant component. We can find a blue node here in the top right of this giant component. There is a blue node connecting many pink nodes, which is a guy has romantic relation with many girls. And also we have girls that can have the interconnection with many boys. So here's the real world situation. We can see that it is not like what I have observed before, that basically all the nodes have similar number of connections. We can see that some nodes have much more connections than others, and some has 1 to 2 connections. So this is the real world case. So we can assume that as our assumption is behavior creates structure, we can assume that from this structure, we can assume the behavior that creates structure is something is the romantic romantic relationships, and romantic relationships have some bias compared to randomness. That some people are favored in the romantic relationships. That is the behavior that creates structure. And what we can observe, even if we know nothing about romantic relationships, we can observe this from this structure. And this is how network simulation works. So the thing we have just, the network structure we have just observed is the Jefferson High School model is called preferential attachment model. It has different assumptions compared to the random model. So again, suppose we have a group of nodes or people, and two nodes are connected by an age or relationship initially. So here is what is different from the computed random model is that now in the computed random model, no nodes are connected initially, but now we have two nodes that are connected by an age initially. So why is this different? Is because we have to have that connection to run the assumptions later, which is at each time step, one pair of unconnected nodes are picked and get connected randomly, and the nodes change of being connected. Sorry, this is a typo. It should be chance. And node's chance of being selected is directly proportional to the number of ages it already has. What does this mean? This means that, so unlike the random model where all nodes have the same chance of being picked and connected, here, then they have different chance of being picked and connected. And how is that different? It is directly proportional to the number of age it already has. So that is why we have to have two nodes get connected initially. Otherwise, there will be no nodes to be picked. So, they will be, as they will be directly proportional to the number of age it already has. So we can assume that it's called the first movers advantage. So if one nodes are connected with, so like if a boy has, like we observe in the Jefferson network, if a boy has a romantic relation with a girl and he has another romantic relation with another girl, it's likely that he has some charming points that attract the attraction from the female. So that make him in an advantageous position and attracted many girls and have many more connections. So this is accumulated advantage. So since a node's chance of being selected is directly proportional to the number of ages it already has, we can naturally assume that different nodes will have different total number of connections at the end of the network. So it will be like, look like that. So we can see that the red nodes in the center have many connections, whereas the red nodes as a perisphere of the network will have one or two connections. So how does the node in the center develop many connections? Is that because it's the chance of it being connected is proportional to the age it already has. So as it develops some ages earlier, it will attract more and more connections and have the accumulated advantage. So I'm going to move to the degree distribution, which is how we can reflect on this difference. So what is degree? The degree of a node in a network is the number of connections it has to other nodes, and the degree distribution is the probability of distribution of these degrees over the whole network. So if one node has 2 connections, its degree is 2. And if one node has 10 connections, its degree is 10. And degree distribution is the probability distribution of these degrees over the whole network. So which in the simple words, which means it is how different nodes have different number of ages. So here's the degree distribution of networks generated by a random model and a preferential attachment model. So in the left is the result of a random model. It has a degree distribution that will take the shape of a bell curve. So which means that most nodes have the same number of links as we observed before. And there's no highly connected nodes and no very poorly connected nodes. So mostly the nodes have exactly the same number of connections, and so they have a bell shape and they're concentrated in the center. However, In the preferential attachment model, it will have a power law distribution, which means that very many nodes have only a few links as we observed in the peripheral of the network, but a few hubs with large number of links as we observed in the center of the network. So these few hubs will be the first most advantages. So as they first develop several connections, and the chance of it being picked in another new connection is proportional to the age it already has. So this will be keep getting attention and has more and more connections. So these few hubs will have a large number of links. So unlike the bell curve here, so which has most nodes have exactly the same number or very similar number of connections, in the power law distribution or in the preferential attachment model, the few hubs will have a large number of links, while many more others will have only few links, and so we have a very different distribution. So this is the main characteristic of a network. So and this is something we can observe. Since we can assume that the preferential attachment model will follow a power law distribution. If we observe a power law distribution in our network simulation, we can assume that the behavior created basically follows the preferential attachment model. So here's again, it is a behavior create structure. And what is the real world case? So here in the left side, in the bottom left is a case of the bell curve or a random model. So in which case, each US city will have basically the same number of connections. We can see that every city will have 2 or 3 or 4 connections with a really similar number, and most nodes have the same number of links. But in the bottom right, we can find that it is more close to real world actually. So the number of links significantly, we can find that some few hubs have significantly larger number of links. Here is Los Angeles, Chicago, Atlanta, New York, and these cities attract more attention. So since they are, again, how did they develop this advantage? Since they have some first connections and the chance of them getting a new connection is proportional to that, they're receiving more attention and getting more connections. So this is close to the real world case. We can assume that exactly these big cities have more transportation connections. So this is a basic idea of the network simulation. To just go back, we just assume the behavior creates structure, and from the structure we can observe how the behavior creates them. And we have 2 assumptions, which is a basic random model, and the second is a preferential attachment model, where the chance of a node getting connected is proportional to the ages it already has. So I'll move back to the navigation, and I'll leave for 5 minutes Q&A session about the basic idea of the introduction of the network simulation. Is there anything you're unclear of, or something you would like to ask? I'll pause here for 5 minutes before we. After that, we're going to move to some hands-on example with programming.
I think there were no questions in the chat so far. But maybe we wait for a minute to see.
I'll wait for a minute, okay.
Yeah, some questions come up. In the meantime, maybe you can, because many historians are actually working with 2-mode networks as well. So maybe you could elaborate a little bit on how random modeling and 2-node networks, how that goes together. Because then obviously not every node can be connected to every node, right?
Yes, this actually, I'll show it here. So since not every node is connected to every node, so if we keep iterating, it will end up with every node connected to every node. But in the real world case, we'll post much earlier than that. So like this figure shows. So if we end up here, we can say that on average, each node will have 2 or 3 or 4 connections, or 1 actually. So if we post here, we can see that how the degree is distributed. But if we keep iterating, so if we again we keep picking two nodes that get connected, and keep picking two nodes that get connected, so it will end up with getting all connected. Every node is connected to every node, but this is not the case since we are going to end up much earlier.
There's one more question by Lu Huang in the chat.
Yes.
Or in the Q&A window. How to set the probability of the chance of a node to be connected?
Yes, that's a good question. How to set the probability of the chance of a node to be connected is we're going to showcase that in the programming. But the probability of the chance of node to be connected is actually determined by the model you are using. For example, in the random model, the chance of each unconnected node being connected is exactly the same. For example, if we have 10 nodes in the network, and there are 45 pairs of unconnected nodes pairs, and so each of the pairs getting picked in each time step will be 1 out of 45, so they will have exactly the same chance. But in the preferential attachment model, as we mentioned, it's proportional to the number of edges already has. For example, if a node has 3 edges and the other one has only 1, it has 3 times as much as the later one to receive a new connection. And so, for example, we have 10 nodes which have 45 unconnected edges. So that will be 1 out of 45 and multiply 3 approximately.
Yes, there are no more questions in the Q&A box, so I think.
And I move to the next part. Here, has an example. So how can this network simulation contribute to our study on historical networks? So in my study, to understand the dynamics of the generated structure of the network, we use an evolving network model to simulate the evolution of the social network. The preferential attachment model is used. This is a reasonable hypothesis, given that people with more connections are generally more likely to develop more connections with others. So this is an assumption based on our real-world observation. But this hypothesis can either prove or disprove by the model. So we are not assuming that this should be correct, but we are trying to verify whether it's correct or not. So we generate a network based on the preferential attachment model and compare the degree distribution of the network with observed network in the tails of the world. As we stated before, so the degree distribution is something we can measure mathematically. And if we do find that, as we mentioned, a power law distribution, which is very few hubs has many connections, and most of them have only few connections, as we mentioned before, like the Chicago, New York example, we can see that we will basically verify the results that it follows the distribution created by a preferential attachment model. And if it's not, especially if they follow a bell curve, which is the behavior, we will assume, which is the typical case of the random model, we will assume that it is, we will disprove our hypothesis, and we will say that it is not created by a preferential attachment model. Actually, in the network, they have similar chance of being connected. Or they can have many, many other models, but we will say that if they follow the same similar degree distribution. So why is this useful? Is that we're going to understand the dynamic that created the aristocratic social network, which is what we're really interested in. So if we can say that the aristocrats, for example, from the great families or the powerful people, if they received more attention, much more attention than others, I will say that it has something like preferential attachment model. And if we observe a preferential attachment model, we can verify that what we are really interested in is that what is the dynamic that created, which is the prestigious people receive attention. So let's try to do some coding now. So please download the following document in the shared folder. Open your Jupyter notebook, create a folder. I'm going to do that later. I'm just first briefly showcase what we're going to do now after a second, and upload both documents to the folder. so which is network simulation data and workshop network simulation. So the first one is data, and the later one is the programming code, the notebook we're going to use. And then you open the IPyNB file and run by putting the cursor in the chunk you would like to run, click run. So you can open these slides. I have already shared that in the shared folder, and now I'm going to share what I've done with programming. Okay, so now create a new folder at the bottom right, at the top right, new, then folder. And you may find that in the untitled folder here. You may change that, rename it to something like HNR workshop. And then open this folder by left click it. And then upload everything. Upload the thing you have just downloaded, the two file, so which is the IPyNB file, workshop network simulation. Click that and then upload. And then upload again the data, which is network simulation data. Click it, open, upload. So this is all we need for this part. And then we can click the IPyNB file. So here's the notebook. I'm going to showcase how I did network simulation. And if you do not understand something, it will be fine. I will add notes after each line to explain what each line is doing. And then if you cannot do that, if you cannot follow up, I will try to let you follow. But if you cannot, it is certainly okay, and you can do that after the workshop. And then since I have already the code here, you do not actually need to actually write anything, but you just need to understand what everything is for, and you can further edit it later. So first, the first chunk. So this thing is called chunk. And you put your cursor here in any place in the chunk and hit run, and it will run. So this chunk is aims at importing the data. So I first import pandas, which is a library, and which is used for reading the CSV file. And here is the code for reading the CSV. So which is pd.readCSV, and this is data we have just uploaded. And I set encoding equals to GBK, which means I will try to include some Chinese characters to be read. So here, this line is used to load data, and then I show the data. It's like that. So this is what we have in the CSV file. So here's the relationship data of the aristocratic social network in the Eastern Jin. So P1 is the first person, P2 is the second person, and A is the relationship is a strong positive relation, and B is weak positive relation. So we have data now. And then in the second chunk, we use to generate the list of people in the network. Again, put cursor here, hit run. So P1, I first convert the P1 in the data frame, so which is these things, Xi Jian, Zhou Zhen, and others. And then here, I convert it to a list, which is a Python data structure. And I convert P2 also to a list, and then concatenate these two lists together. And here, I'm going to say how many people we have here, which is 1,472. So here is the output in the Python, in the Jupyter Notebook. I have 1,472 people. We do not have that much people, since one person can be connected multiple times. For example, Xi Jian here appears 2 times, and he will appear 2 times, so it will be calculated twice in this calculation. So then we have to remove the duplicates by list set function. And now we have node num, which says the number of people, the number of people now in the network. And print that, now we have 250, which is the real number of aristocrats in the network after removing the duplicates. And the print people, like let's say how the people looks like, is a list of people's name, which has 250 of them. And the third chunk we use to generate the matrix of people's relationships. I first import NumPy as NPs, which is library for creating relationship matrix. And then I create the relation matrix by np.zeros, so which is I created 250 multiplied 250 empty matrix. So each of the, they have 250 and 250, multiple of 250 elements, and every element is 0. And then I'll loop through each line in the data. So here, each line data is the relationship as we find here. So here's the data. And for each line of data, I get the index of P1. I got the index of P1 in the list of people. I got the index of P2 in the list of people. And assign the value, which means P1 has relation with P2. So as we have here is np.0, which is initially they will be 0. And then now we set this to 1, which means that they have relationship. And correspondingly, we assign value, which means P2 has relation with P1. Here, for the pairs of people with multiple relationships, we assign value for 1 for multiple times. But this will not create problem since the value is still 1. So since initially they will be 0, and we assign 1 to them, and it becomes 1. And we assign 1 to them again, and it will still stays 1. And we're going to see how large the matrix is, which is 250 multiplied 250. So which is actually we created here. Len people is 250. And here is how the relation matrix like. It is like that. 250 multiplied 250, we have omitted here. But there's not actually all zeros, so some of them will be 1 if they have relationship. And also we're going to print how many edges in it in the relation matrix. We have to divide 2 since a relationship of what P1's relation with P2 is the same relationship as P2's relationship with P1. And the number of total edges in the network is 505. So which is correct. But it's different from here, which has 736 edges, relationships here. So this 700 relationships created 500 700 relationships create 500 edges because some pairs of people have multiple edges, and those multiple relationships, and they will have only 1 edge connected by 2 nodes in the network. The fourth chunk is used to generate degree distribution. So I first created an empty degree dictionary to record the number of nodes of each degree. So here, the key, so in the Python, the dictionary is another data structure of Python. It has a key and a value like that. So here it is key, and here is a volume. It is a value. So here, in this dictionary, the key is a degree. So which is number of, so degree means number of edges a node have, and the value is the number of nodes with that degree. For example, if we have 3 nodes with degree 5, we will have degree 5 as key and 3 as a value. And here we look through the relationship matrix, which is this one is the relationship matrix. And for each node or person, its degree is the summation of the line or number of its relationships. So we will sum these things up. So here's a line. So this is a relationship of the first person. We're going to sum this up as a total relationship he or she contains. And we will add 1 to the number of nodes of that degree if there are already some nodes. And assign value 1 as the number of nodes of that degree if there's no node. So here's something, a trick we deal with Python dictionary. So if this dictionary has already a key, we assign 1, we add 1 to them. And if it doesn't have, we assign 1 to them since it's not initial 0, it's initially empty. So we assign 1 to make it not empty if it is the first case. And now the dictionary looks like that. So here, this means that there are 21 nodes with degree 3, 110 nodes of person or people with degree 1, 2 nodes with degree 16, etc. And then we sort degree distribution. So which is I sort the dictionary and reorder it by the degree number. And here's what it looks like. So which means that we have 1 node with 53 degrees. So he should be a very powerful person in the network. 1 with 35, 1 with 31, and at the bottom, 110 with 1, 52 with 2, and 21 with 3, as we observed already here. So these are exactly the 2 same dictionary. We just printed it out by sorting them differently. And then here, we generate the nodes and the number of nodes of each degree. So we unzip the tuples to 2 lists. So here is a tuple. So here, this one is called a tuple, which has 53 column 1. And we unzipped the tuples to 2 lists separated by comma. So here we are going to 553, 35, 31. We converted it to here at least 53, 35, 31. And also here 1, 1, 1, 1, 2, and we converted here to 1, 1, 1, 1, 2. The first list is degree, and the second list is the number of nodes of each degree, and we print them out. So let's move to the visualization part. So here is a library matplotlib where you use for them to create visualizations, and matplotlib inline is used to display it. I said the style of ggplot is not necessary. I just make it more visually acceptable. And then plot a scatter plot of the degrees in the x-axis as the number of nodes in the y-axis. And I set the label of y-axis as the number of nodes. I set the label of y-axis as a degree, like here. So here we can see that it is very similar to we have introduced is a power law distribution. We can basically we can try to assume that it has something similar to the power law distribution. But this is only preliminary assumption. We're going to verify it with the real power law distribution or created by preferential attachment model. So here, so this is the observed network, what we have in the Shishuo Xinyu. But here, we're going to create another network, which is fictional and completely generated by the mathematical assumptions. So a preferential attachment model. This is something more a little bit demanding, but I'll just basically explain its basic idea. You may just get the it's basic. It will be certainly fine for you not to skip the details and understand the basic idea. So here, I include the libraries math and random for generating the random number. And here, this is by definition here, this is I generate a function. So which means I take an input, which is a k, and return a value. Here's something it returns. I first created a dictionary of lists and the total number of nodes in the network. So here's 250, actually this number is 250. And then I set the I links, the initial number of links in the network as 0. So here is what we have already introduced in the preferential attachment model. So initially there have been no connections. And I loop through all the nodes and initialize the node I with an empty list, which will record its link with all other nodes. And for each node in the dNetwork.values, which means that, so again, so this is the first loop of all nodes. And then this is the second loop. So we have a loop inside the loop. Since one node connected to all nodes, and we want to record the nodes of its connection to each node. So one node have 250 potential connections. So here, I set a threshold with the proportional to its current degree plus 1. So here, this one is its current degree, and I plus 1. And inversely proportional to the total number of links in the network. So here's the total number of the links in the network. And if the random value, which is a random value between 0 and 1, is exactly the same chance to fall between 0 and 1, is smaller than threshold, I will add a link between this node and node I. And I will add 1 to the total number of links in the network. So we can say that if this threshold is, for example, is 0.9, this thing is very likely to happen. And if this threshold is only 0.1 or 0.01, this thing is not very likely to happen. So in this case, we are getting the assumption of the preferential attachment model, which is the chance of a node receiving a new connection is proportional to the nodes, to the connections it already has. I then calculate the degree distribution and return to this degree distribution. And this chunk, I run the preferential attachment model. So here, K is a parameter which influences the F threshold. So that's the probability, influence the probability of generating the links. I set the k equals to 2 below, but you can try to change number and see what will happen. Actually, they will basically the same thing, but they change the number of the threshold, so it will have some difference in the power law distribution, but it will be still a power law distribution. I get the degrees number of links generated in the preferential attachment model, and I duplicated what I have done in the chunks 4 to 6 here, so which is general degree distribution, source sortage, and generate the nodes and number of nodes of each degree. So here's something the same as we already have in chunks 4 to 6. And then I actually run the thing. So initial I-links equal to 0, and while the I-links is not the same as the H-num, so we're going to continue to live until it reaches the same number. So we'll simulate the network so that it will have exactly the same number of nodes already guaranteed, since we have this node num, which is 250, which is number of nodes in the network we already have, and the edges in the observed network. How do we guarantee the edge will be the same? I'm using this command. So which is, if it's not the same, I will continue to loop through it until it reaches the same number. And I run the preferential attachment model until it reaches the same number, and I print the I-links. So here it is, the first loop is 495, so which is, I use 250 nodes, and I run the preferential attachment model until it reaches the end up time. And the first time it has 495 nodes. That is not what we want, since we want the edge to be exactly the same as 505. And I continue to run it with the same command until it reaches 505, which is what we want here. Then I will visualize both the simulated network and the observed network. I set the color here to differ them. So the simulated network will be in color red, and observed will be in color blue. And again, the labels and the legend. So here we can see that they are really similar to each other. So the blue is the observed network, and the red is simulated network. And then we try to connect them with line plot. So here's the scatter plot of different scatters, and here's the line plot that connects them together. So we can see that they are very same. But there has some difference for sure. The simulated network has a longer tail in both ends, so actually we do not have nodes with 160 degree in the observed network. The largest one would be 53, I think. Yes, 53. But here we have one with we have one with more than 80 degrees in the simulated network. But basically, they are really similar to each other. So now we can say that we can conclude our hypothesis is verified that this is a preferential attachment model, or at least we can say that the network in the Shih-Shuo-Xinyu is very similar to a preferential attachment model, since they have followed a very similar degree distribution. So what's the assumption of degree distribution? A preferential attachment model is that a person or a node receive new age is proportional to the age it already has. So we can say that the prestigious people in the Eastern Jin dynasty, as recorded in the Shih-Shuo-Xinyu, actually receives more attention and will receive more and more ages. So that is the behavior generated the structure, and that's actually what we are interested in. And this provides some insights to the Shih-Shuo-Xinyu social network. So here's what we have done. And I'll pause here to wait for some questions. And here's a question. I wonder whether this model will take parameters to simulate the network with weighted degrees. So weights of degrees I mentioned also indicate preference. Yes, that's an excellent question. This model can take parameters with weighted degrees, for example. But I'm just demonstrating the very simple case, which is an unweighted network. But for sure, for example, one person can connect it to person A very heavily, but very only lightly to person B. But these two ages should be different. We can take that into account as well. But yes, this is practical in preferential attachment model, and I'm just not demonstrating that in this simple case. Do you have time parameter in your data? If I have a historical network to spend 2 or 3 centuries, it's okay to similar approach. Yes, you can. Since again, the social network I'm doing is a topological structure, which is not actually directly taking time parameter into account. But as historians, we have to deal with that. So, so that happens after the model. That doesn't happen in the preferential attachment model simulation case. It happens in the interpretation. So, if we are using the historical network that span 2 or 3 centuries, and we do find some preferential attachment some patterns that follows preferential attachment model, we can say that we have to still to be careful about our conclusions, since they have spent 2 or 3 centuries, which means that the first person in the, for example, in 7th century, is not possible at all to connect to the person in the next century. So even if they follow or doesn't follow, we have to be careful about our conclusions. But this not happen, but that does not take place in the simulation part, but in the interpretation part. Okay, since we do not have much time, I'm going to move to my slides. So as for conclusion, in the network simulation, we have only showcased very basic models, but there are many more models, like small worlds, which small world is actually what a simple, a common assumption in our world, which is like a person should be connected. So we are living in a small world that your friend's friend of friend, you something you think you should hardly have any connection with is actually your friend's friends or friends' friends. Or it seems that you can connect any person in the world with 6 connections. So if we are using this assumption, we'll assume that the network is interconnected and they are not very far to reach each other. And team assembly and various network extra. And I'm not going to show this in details, but you should keep in mind that I have only showcased 2 basic models. They are not the whole story. There are many, many more models. And in addition to directly programming, a software NAT logo is also useful for network simulation, which you can download here from Northwestern University. Why I'm using Python to demonstrate that Python got some flexibility. So since I can exactly simulate it and change the parameters what way I want, and simulate it to have the exactly same number of edges and nodes as a Shih-Tzu network to assume that they have exactly the same assumption. But this NAT logo thing is something really fun, and you can play with that after the workshop. It has a very powerful tool for network simulation as well. The second part of this workshop is exponential random graph models, which you may find it hard to understand, but I'm going to explain it. And then I'm going to, again, have introduction part and a hands-on example. First, introduction. Again, let's begin with some assumptions. So the first assumption in the ERGM model is that network is a realization of random variables. Some pairs of nodes have connections, while others don't. So since in reality, a network is not completely unconnected and not completely connected, or it will have actually, it doesn't make much sense for interpretation if that is the case. So in real world, most networks have some nodes connected while others not connected. So we'll be interested in what kind of nodes are connected, or what kind of pairs of nodes are not connected. So this could have something to do with some attributes of the network. Since we have this first assumption that was the realization of random variables, we're going to investigate through these variables. So the idea of exponential random graph models, I will call it ERGM from now on, is to predict the presence or absence of the NH based on certain attributes. Since some edges are connected and others not, we're going to investigate which ones are connected and how can this be explained. It models the whole network rather than the relationships between variables. So the ERGM is based on attributes. So we are going to since we're going to predict the presence or absence of age based on the attributes. So the attributes are something we are really interested in. In ERGM, attributes can be basically divided into 3 categories: age-based, node-based, and structural. I'm not going to explain it in too much details, but I'm going to showcase the basic ideas. So the age-based attributes is to investigate how if we are going to predict the presence or absence of age based on some age-based attributes. For example, the mutual means that the tendency for mutual ties in a direct network, which means that, so if we have in a direct network, which is A connected to B is different from B connected to A. So this means that if I have A already connected to B, this means that B has a more chance to be connected to A compared to B and C connection. So this is mutual means. And I have some node-based attributes. Node match, which means that, so if I'm going to create some more attributes on the node. For example, if I can have male and female. If a node is male and the other one is female, does this mean that they have more chance to be connected compared to both male nodes or to both female nodes? So this is node-based attributes. And structural attributes is something more complex. For example, the transitivity means that if A is connected to B and B is connected to C, does this mean that A has more chance to be connected to C, since a friend's friend is more likely my friend, or a friend's friend has exactly the same chance of a random person to be my friend, or they have a less chance to be a random person to be my friend. So this is structural attributes. And I'm going to do is to work with a node-based attribute. In my study, we use exponential random graph models to assess whether presence or absence of an age can be explained by the node attribute family affiliation. So here, as I demonstrated before, I'm going to use a node-based attribute, and I'm going to use node match. So first, we set a baseline model in which only an age term is specified. So the age term in the ERGM model means that the number of ages in the network. Since the presence or absence of an age is certainly have something to do with the total number of ages in the network. For example, if I have three people in the network and they have 0 to 3 possible ages, and if I tell the network they have 2 ages in total, it's certain that the presence of a random node, a random age is 2 out of 3. If I tell the network we only have 1 age, this should be 1 out of 3. So here, the total number of ages is directly related to the absence or presence of a certain age. So here is the baseline model. And then we added a new variable, which is what we're really interested in, is node match family affiliation, which means that whether the 2 nodes have the same affiliation, which is whether 2 people come from the same family, has something to do with their absence or presence of the age of an age. So we're going to evaluate in other words, we're going to evaluate whether nodes from the same family have a higher probability of being connected, or higher, or average, or actually lower of being connected. So here we're using node match, which means that whether the 2 nodes have the same attribute. And the attribute we're using is the family affiliation of the aristocrats in the Eastern Jin social Xinyu network. Again, we're going to move to the coding part earlier, since ERGM, I have skipped the statistical things and only explain the basic idea of ERGM. First, please download the following documents in the shared folder, as Professor Chen Song shared. Save them in a certain folder, open workshop ERGM R in RStudio, and change the directory in lines 4 to 5 from ... to the directory where you just save the files. Here are the 3 files you have to download, which are 2 data files, 2 CSV with the data, and the workshop ERGM is R script you're actually going to run the data. And by putting the cursor in the line you would like to run and click run or Control plus Enter, you're able to run something in the RStudio. Now you should be in the same page as I am. We're in RStudio. First, as I mentioned, you have to change the data directory here in lines 4 to 5. So where you should change this 3 dots to where you have just saved the two data file, ERGM data family and ERGM data relationship. For me, it is saved here, but you might save something in somewhere differently, and you have to change it to the directory you just saved it. And you may change the / to / since / means something differently in R. It's called escape character. After you have changes, you can run it now. Let's run it line by line. Move the cursor on that line and click run. So in this line, it's going to take some time. We're installing the package .NET in ERGM. So this is something containing the ERGM script. So we're not writing the ERGM, the mathematical details in ERGM in person, since we're going to use some package already be written by others. By the way, Splat is a very powerful package. I strongly encourage you to download it. So that's the reason I didn't directly install ERGM, but install the whole page.NET. So we can see that the console here, the R is busy running that to installing the packages. Here we can see that this small colon, this small character, and this means that we can run the next line now. And then we update the package to make sure that everything is up to date. And then we load the libraries that we just downloaded. We have already loaded that. And then now the thing we're going to really want to run. So load the nodes. So we have 250 in the bottom right. We can find the data here. We have 250 nodes, which is 250 people. We have just already defined. And links, which is 505 links, as we have just already defined of 3 variables. And now we have the nodes and links, and then we build a network with the .NET, so which is network command function. Now we can find out here's a network. And then this line, line number 7, we use to set the attribute family as a value in family column in nodes data. We already have a family in the nodes. We show their family attribution, and we set that. We try to concatenate that to the SSXY network, which is we tell the program that we have an attribute which we can find in the nodes data. Run that. Now we have everything we need. So we have a network with 250 nodes of people and 505 ages of connections. And then we have, for each node, we have a characteristic, which is an attribute, which is family affiliation. So for each person, we have his or her family as affiliation, as an attribute. And then now we're really running ERGM. So ERGM is a command in R. So which this is actually abbreviated from the .NET here. And here's the baseline model, which is only how ages. So the total, which means the total number of ages. And we're going to say that how, if we're only using total number of ages, can predict the presence or absence of a node, of an age in the network. Run. So after it's run, here I'm going to show the summary of what we have just run. So here is what we have. I'm going to explain it in details later. So just remember this number. We have the ages estimates minus 4.1. And here is a standard error. And Z value, and the PR means that which is very significant, which means that the number of ages is significantly related to the probability of a presence or absence of a certain age. This is certainly true in most cases. And this is not what we're really interested in. What we really are interested in is the node match family. So run that. And summary. So here, the ages number changed from -4.1 to -4.13. It's not much big, not a big change, but the node match family appears. It is 0.78. I'm going to explain this number later. And it's also significant, though less significant than the ages. So the ages should be very, very significant, since as I explained, the total number of ages is certainly related to a presence of certain ages. And here, although it's not that significant, it's still very significant. Which means, so what does this mean actually? It means that it is a statistical test to measure randomness. So which means that if we do a random experiment and it has a more significant result, the probability of having a more significant result is 0.00018, which is a very, very rare case to have a more significant result, which means that this result is not likely due to randomness, but it really has something to do with node match family. So here we have finished running them, and I'm going to go back to the slides again and explain what this means in details. This is the data we just observed. So here means that the probability of forming an age or relation between two random nodes of people is an exponential function. So this is why ERGM is called exponential random graph models. It's 0.016. So we convert, so here's -4.10. We convert that with this function to something we can understand, which is the probability of forming an age, which is 0.016. And here is the model we run later with the ERGM, with the node mesh family affiliation, which means that, again, the two random nodes forming an age is 0.016, and the probability of forming an age between two nodes that share the same family affiliation is, we can find here, -4.13, which is here, plus 0.78, which is in the second line. And here it becomes 0.034, twice as high as the one we do not include node mesh. So which means that if two people are from the same family, they have the same family affiliation, they have a node mesh in family affiliation attributes, they exactly have the more probability to be connected. And so this how large they improve is twice. So here's what statistics tell us. Why is this important? Is that since in the real world, we have a network and we have some attributes. All these simple attributes like that is what we show here. Sorry. What we show here is node mesh, but we can find many other patterns as well, like transitivity, triangle, or some mutual age factors in directly network. So since we have this many things, we want to predict how this is related to the, how can we predict the network structure based on these attributes. So in our case, in the Shishou network, this result tells us if the two people from the same aristocrat family, they have more chance, but not very, very significantly improved, twice as much as the original one, to be connected compared to random nodes. We can, from this data, we can measure the homopholy of the network, which means that how the network tells us if two people from the same family have to increase the probability of them being connected. For example, if we assume a very network with very strong homopholy, like people with usually connected to people with their same family, but rarely connected to other families. We can assume that this assumption, these results will be very high. For example, if there's a 0.1016, this could be 0.1, 6 times as high as the original one. Indeed, we can see that this is a very strong homophily. And now we can observe this is a weak but exists homophily. But if the number is exactly the same or even lower than that, we can see that there's no homophily, and even a negative homophily, that people are usually connected to people with different affiliations, which could be a case in the romantic network with gender as node attribute, as node match. As in most cases, people have romantic relations with other genders, which has a higher probability. Finally, for concluding, we have only explained the basic idea of ERGM and showcased a basic example without diving deep into its statistical assumption or advanced usages. For further instruction about ERGM in R, which is we just ran in the RStudio, you may refer to the official document detailed here. And additionally, a Python implementation of ERGM is also available, though it's much simpler than R package, but again, it's written by someone. So we can, if you want to see the statistical details, this is something you may want to refer. And this is all for my workshop. And I would like to acknowledge the design of the introduction section of this workshop was strongly influenced by the course materials used in the network analysis course taught by Professor Yana Disner and Dr. Candidate Li Ding from the University of Illinois at Urbana-Champaign. And again, you may contact me for anything, including programming, introductory notes, and the statistical assumptions about the network simulation ERGM. I'm happy to answer them.